Partitioning methods are another way to cluster data. Two primary methods include k-means clustering and partitioning around mediods clustering. K-means clustering requires that k, the number of clusters, be pre-specified. Once k has been determined, initial clusters are defined, usually at random, and each object is randomly assigned to be a member of one of the k clusters. Then the method iteratively proceeds as follows. In the first step, the center of each cluster is calculated. In the second step, for each object, the distance between that object and the k centers is calculated. In the third step, each object is assigned to that cluster, which minimizes the distance. Steps 1 through 3 are repeated until no assignments change. That is, none of the movements will further reduce the sum of squares. K-means uses the squared Euclidean distance as the distance metric. On the left-hand side, the data are plotted where the points represent the observation number. Suppose we set k equal to 2. Then we randomly assign observations to clusters, and suppose that observations 1, 3, 4, and 5 are initially assigned to cluster 1, and the remaining observations 2, 6, 7, and 8 are assigned to cluster 2. In the first step, we calculate the cluster centers, which are these points, for cluster 1 and cluster 2. In step 2, the distance between these cluster centers and all observations are calculated. In step 3, each observation is assigned to the cluster that minimizes this distance. In this case, observations 1, 3, 7, and 8 are assigned to cluster 2, while observations 2, 4, 5, and 6 are assigned to cluster 1. Then, the new cluster centers are recalculated using the original observations of the new cluster members. The process of calculating distance from all observations to the cluster centers are repeated, and cluster assignments are updated by assigning individual observations to the cluster with a minimum distance. For this example dataset, there are no changes in the cluster assignment in the second step. However, in other applications, the clustering result may depend upon the initial cluster centers chosen. Therefore, it is customary to use several different initial starting values. Clusters that consistently emerge are then regarded as reliable clusters. The k-means function in R can be applied to perform k-means clustering. As you can see, observations 1, 3, 7, and 8, and observations 2, 4, 5, and 6 form the k equals 2 clusters, and the cluster centers are indicated. A plot of cluster membership and the centers can be displayed. As you can see, the cluster center is not among the observed data points. In partitioning around mediods, rather than use means of currently defined clusters, centers for each cluster are restricted to be one of the observations assigned to the cluster. Thus, there is no need to explicitly compute cluster centers. Therefore, partitioning around mediods can be used when only distance or dissimilarities are available, whereas k-means requires the raw observations, since calculation of the average is performed using the original observations. For partitioning around mediods, for a given cluster assignment C, find the observation in the cluster which minimizes the total distance to the other points within the cluster. For each of the k clusters, these will form the k-mediods. Given a current set of cluster centers, or mediods, minimize the total error by assigning each observation to that cluster with the minimum distance. That is, reassign each observation to the closest medioid. Steps 1 and 2 are repeated until there are no changes in cluster member assignments. The cluster library includes a function PAM for partitioning around mediods. The data object is supplied and the number of clusters is specified. The summary function displays several results of the PAM clustering, including identification of the mediods, the cluster assignments, where again observations 1, 3, 7, and 8 are in one cluster, and observations 2, 4, 5, and 6 are in a second cluster. Note that there is no inherent meaning in the cluster number. A plot of the data and identification of the mediods more clearly shows that the medoid, or cluster center for PAM, is indeed an observation in the dataset. For partitioning methods, K is a parameter decided by the user. Note that not all values of K result in natural groupings. It is therefore advisable to run the algorithm several times with different values of K and to select the value of K for which certain characteristics or graphics look best, or to retain the clustering that appears to give rise to the most meaningful interpretation. That is, K can be decided by trying all or many possible values of K, then selecting that K which is best relative to some numerical criterion. It is permissible to try several algorithms on the same data because cluster analyses are mostly used as a descriptive or exploratory tool, in contrast with statistical tests, which are carried out for inferential or confirmatory purposes. One way to assess the goodness of fit of a given clustering is to compare the size of the clusters versus the distance to the nearest cluster. If the intercluster distance is much larger than the size of the cluster is deemed to be trustworthy. The ratio between the distance d to the nearest cluster center and its diameter can be calculated for each cluster and used as an indication of cluster quality. One measure is homogeneity, which is the average distance between each observation and the center of the cluster to which it belongs, given by this equation, where n is the total number of observations to cluster, x sub I is the vector of measurements on observation I, and c represents a cluster center, and d is a measure of distance. Another measure is separation, which is the weighted average distances between the clusters given by this equation, where n sub A and n sub B are the number of observations in clusters A and B, respectively, and C represents the cluster centers for clusters A and C. For estimating the appropriate number of clusters, one can estimate homogeneity and separation for various values of K and look for a leveling off. Silhouette is a composite index reflecting the compactness and separation of clusters and can be applied to different distance metrics. Let A denote the assigned cluster for observation I. Then A of I is the average dissimilarity of object I to all other objects in its assigned cluster A. Assume that A is not a singleton. Now consider cluster C, different from cluster A. D of I and C is the average dissimilarity of object I to all objects in C. After computing this distance for all cluster C that are not the assigned cluster A, let B of I equal the minimum distance from object I to all other clusters other than the one to which it was assigned. That is, cluster B, for which this minimum is attained, is called the neighbor cluster of object I. In other words, cluster B would be the second best choice for assigning object I. Then S of I measures how well object I matches the cluster assignment at hand. Note that silhouette values are between -1 and 1. When the silhouette is close to 1, the within dissimilarity of object I to other objects in the assigned cluster is much smaller than the dissimilarity of object I to the nearest neighboring cluster, indicating that object I is well classified. When the silhouette is close to 0, the assigned cluster and the nearest neighboring cluster are approximately equal, indicating the cluster assignment of object I is somewhat arbitrary. When the silhouette is close to -1, I is closer to the neighboring cluster than to the assigned cluster, indicating that object I is misclassified. The silhouette coefficient when n objects are clustered into k clusters is given by this equation. The silhouette coefficient, also called average silhouette width, of a cluster can be used for assessing the strength of individual clusters. Silhouette estimates are provided as part of the PAM function. This information is output when applying the summary function to a PAM object. Kaufman and Rousseau offer this subjective advice for interpreting average silhouette width for the entire data set. If the average silhouette width is between 0.71 and 1, a strong structure has been found. If the average silhouette width is from 0.51 to 0.70, a reasonable structure has been found. If the average silhouette width is from 0.26 to 0.50, the structure is weak and could be artificial. And if the average silhouette width is less than or equal to 0.25, no substantial structure has been found. When applying the plot function to a PAM object, two plots are produced, the second of which is the silhouette plot. The silhouette plot is a plot of the silhouettes ranked in decreasing order for all objects assigned to each cluster. Notice there are 4 observations in 2 clusters, and the average silhouette width for each cluster is given, both of which indicate a strong structure has been found. The average silhouette width can be used for selecting the best value of k. For estimating the appropriate number of clusters, one can estimate the average silhouette width for various values of k and look at what k for which the average silhouette width is a maximum. In this example, we applied PAM using k equals 2, 3, 4, and 5. The maximum occurs when k equals 2. The gap statistic, which is a measure of homogeneity of clusters, calculates a goodness of clustering measure and is used for estimating the number of clusters in a data set. For each number of clusters k, it compares the within cluster sums of squares to the expected within cluster sums of squares, where the expected value is determined by bootstrapping. The clus-gap function in the cluster package can be used to calculate the gap statistic, where the data set is supplied, the clustering function is specified, and the maximum number of clusters is also specified, as well as the number of bootstrap resamples. This package can be loaded to produce a nice graphic of the gap statistic results. We want to choose the k with the first maximal gap statistic, that is, the k before the first decline. Again, we would choose k equals 2. Keep in mind that clustering is an unsupervised learning procedure. If phenotypic data are available, perhaps clustering is not needed. Before the analysis, we may want to know if there are any clusters in the data, and if so, how many. Typically, partitioning methods generate clusters that are often more robust than hierarchical clustering, but clusters may depend on the random start. One potentially misleading artifact of hierarchical clustering is that in the end, all objects are ultimately in one large cluster. It is quite possible that some objects are totally unrelated, yet the algorithm will display them all together. When clustering a large number of genes, a dendrogram may become very difficult to read. This is often alleviated through the use of programs that permit zooming and panning of the dendrogram display, such as the Michael Eisen TreeView program. Also, it is important to note that once 2 observations are clustered or merged together in hierarchical clustering, the decision is final, so poor merges are not subsequently corrected. There is no reason why clusters should be hierarchical in microarray data. It is not natural to impose a nested structure if the primary purpose is to identify naturally occurring groupings in the data. The deterministic nature of hierarchical clustering can cause objects to be grouped based on local decisions, with no opportunity to reevaluate the clustering. Here are some related references.